Swayam Prabha. Digital India. Educated India.
How these things are happening. And now, example number 4 is more of an example, but a kind of answer to that quiz question that we have in the last class. So the question was, we have an amide bond, and these are the alpha carbons, which are actually the chiral. And if I try to find out what are the absorbances coming from a peptide backbone. So this is, we can say, a peptide backbone. And the peptide backbone is mostly amide and this alpha carbon. And the absorbances, we can see, we have absorbances below 175 nanometer, which is coming from N to sigma star interaction. What is the N? N is the lone pair coming from the nitrogen mostly, which is going to this NC sigma star bond, which is coming below 175 nanometer. Very strong UV region. We can have some bands around 175 to 200 nanometer region, mostly around 190 nanometer, which is coming from pi to pi star transition. Where this pi to pi star transition coming? This pi to pi star transition is coming from this carbonyl stretching frequency. So it is a carbonyl pi to pi star transition. And then we have this 210 to 230 nanometer region where a N to pi star transition happens. And that is mostly happening to this nitrogen lone pair to the pi star orbital of this C double bond O. So it is a lone pair of the nitrogen to the pi star of the C double bond O. So this is what is actually happening over there. Now the question is that, okay, that's all very fine, but when we look into the structure very closely, we found this amide bond. And as we have discussed earlier, due to this lone pair interaction over there, it is actually creates a planarity over there. And as we know, a planarity means that is not chiral. So how still a chiral band found over here? It is actually the CD active bands, because when you look into the CD bands, for example, look over here, the CD bands over here, we are mostly looking at very strong CD bands in the region of 200 to 230 nanometer, even 190 nanometer, which are basically the regions of pi to pi star and N to pi star absorbances, which forms this planar amide region, which should be achiral in nature, but it is still CD active. That means somehow chirality is induced over here. And that is the question, why it is happening. So most of you try to write it in a way that it is somehow losing its planarity. So that is not entirely correct, because it actually holds quite a good planarity because of the strong amide bond. And especially when it is forming, some of you write that when it is forming the alpha helix, the beta sheet, that is probably creating some strain on this amide region, and that probably going out of the plane a little bit. Okay, it does put some strain over there, but it never loses the planarity on its own. So one of you also discussed about the Ramachandran plot. So if you look into the Ramachandran plot, you can find that there are two different dihedral planes we can talk about. One is coming from this amide, nitrogen end of the amide, one from the carbonyl end of the amide, and we found there are two different planes. However, if I try to draw a plane considering these four groups, that also forms a very good planar region. So Ramachandran plot is a little bit different because we are talking about two different planes, not this amide bond altogether. So take a look into it later on. So altogether, what I can say, the alpha helix, the beta sheet, obviously it puts strains on that, how it is going to behave, how it's going to orient, but it is not really stripping it out of the planarity. So whoever wrote those particular answers, they got 8 out of 10. Now, some of you try to write that, okay, there is somehow the chirality is induced over there. And the chirality is getting induced probably from this alpha carbon present over there. The alpha carbon present over here, it is somehow inducing some chirality over here. That is partially true. That is somehow one of the induction of the chirality happens, but exactly how? So some of you who wrote up to this point that chirality is getting induced, they got 9 out of 10. 9 out of 10. And then a few of you wrote it very nicely that what is actually happening. So for an example, let me draw the structure of the alpha helix. That would be easier for me to explain. So for an example, this alpha helical structure. So over here, what happens? You can see this amide bond is formed between this carbonyl and this amine. But that doesn't mean that this amine and this next carbonyl is getting out of the plane, or this nitrogen and this carbonyl next to it, it is getting out of the plane. They're remaining in the plane on their own. So this is actually planar, this is actually planar. However, it is still becoming chiral. Why? That is coming because of the overall secondary structure. You can see the overall secondary structure, it is formed over here. It is creating a dipole. These are all dipole interactions, right? Between the carbonyl and the amide group. So there is a carbonyl group, there is a amine group. So it is forming the hydrogen bond. That means it is creating a dipole. And this dipole has a direction. And all these dipole, if you consider together, it is going to create a helical motion of the dipole moment, because that is how it is oriented. That means it is creating a dipole moment which is actually helical in nature. And as you know, once you have a helical in nature, you are creating a chirality. So that is coming from the helicity motion the dipole moment is creating over there. But how it is affecting that amide bond, that is affecting in the following way. So as we know, the nitrogen, it is creating a amine bond over here. So let me just move it over there a little bit. So over here, what happens, this carbonyl, which is going for the pi to pi star interaction, will be going to be surrounded like this. This should be the direction of the dipole moment for the pi to pi star. And n to pi star? N to pi star will happen in the following way. If I draw it again, it will be C double bond N, CO minus, NH plus. So now the dipole moment for the N to pi star will be in this particular region, in this particular line, and pi to pi star in this line. However, those things, because of their planarity and their conjugation, they are going to come together. So you are going to have this particular direction and this particular direction, and all together, what we are going to see is the following. We are going to see a conjugation, a motion like this. This will be the dipole moment, which will be affected by the N to pi star and pi to pi star. It is more of a, these two are actually vectorially connecting together. So that should be the direction of the dipole moment change. And why dipole moment change we are talking about? Because that is the operator for the transition. Now imagine, look into all these C double bond ends. Let me draw it in a fresh one. So if I now draw the alpha helix a little bit bigger now, Now you can see the alpha helical motion. It is actually going through this. This is the dipole moment created by the alpha helical position for this hydrogen bonding network. And the C double bond N, as I just said, otherwise it will be like this if it's pi to pi star, which will be out of the plane. Let me draw that with the red line, which will be perpendicular to this alpha helical motion we have created. But due to this carbon nitrogen interaction and N2 pi star interaction, that is going to be somewhere in between. So instead of having, say, this is the alpha helical one, and this is the of C double bond of pi to pi star, and what we are having something like that altogether. This is the real pi to pi star and N2 pi star interaction when both of them are interacting. And now you can see they are not 90 degree to each other, but some other angle. And if there is some other angle, that means they can have a vectorial contribution together. And that is why this alpha helical motion, which is created by the secondary structure, that is going to affect my alpha helical structure like this. And over here, you can see, or you can imagine, depending on which particular direction it is coming, you can have two different orientation. And that is what it is believed that why we have two different humps at 218, at 208 and 222, because of the two ends of the dipole a little bit differently oriented with respect to the alpha helix, because the alpha helical position, this 1 to 4, is actually repetitive, but they have two different orientations over there. And that is probably the reason why we have two different humps over there. So it is because of the secondary interaction and the normal magnetic moment is actually coming together and playing a role over there. Now, what happens to the beta helix, beta sheet? So now if you look at the beta sheet, now you can be very sure what is actually happening. Now take a look. In the beta sheet, when you form, where is the C double bond O on this side? C double bond N will actually going to bring that over here. And with that respect, you can see the beta sheet, this is parallel, one is anti-parallel. So this is going like this and this. Now they are not perpendicular to each other, or in this case, parallel, and your C double bond N will be like this. So they are actually making an angle which is not 90 degree. And that is why it is going to be not orthogonal and will be going to interact with that. However, in the beta sheet, you can see the interaction of this is mostly one particular angle. No other orientations are possible in this particular orientation. And that is why it is believed there is only one broad hump, the 280 nanometer for the beta sheet. So that is how the overall secondary structure induces chirality in the planar C double bond O or C double bond N form. And that is very much important for the CD spectra, because right now we are measuring the CD spectra in the region of 190 to 230 nanometer region. Otherwise, if it is not possible, we have to go to the region where the carbon bonds are actually absorbing below 175. And that is very tricky to do, because over there, all the gases started absorbing nitrogen, carbon. So it will be a huge background spectra. And it will be very tricky to measure your original signal from there. So that is why, because of this phenomenon of induced chirality, the systems that we are measuring, especially for the protein structure, is actually possible, that we can actually measure it. So this is known as the induced chirality. And there will be a chirality of the alpha helical structure of a polymer that you are taking, and the polymer, because of the alpha helical structure, it is showing some chirality, or a system with a alpha carbon with 4 different groups, it is showing some chiral signals. That is known as intrinsic chirality, which is automatically coming on its own, not induced by other chiral center.